Okay, so today we are going to learn about square root and cube root functions. And we'll start with just square roots. So you're all familiar with square roots. This is one type of a radical. When you don't see the little nth root, it is a 2. Now when we think about what numbers we can plug in for x, we are limited. Earlier this year, we talked about taking the square root of a negative number, like square root of negative 25. And up to this point, you'd learned that you can never take the square root of a negative, not possible. And then this year, last quarter particularly, we learned if we take that negative sign and we move it out front, it becomes an I. And now we can evaluate this and say, oh, okay, this is equivalent to 5i. That's imaginary. You can't see it on a graph. Your traditional graph is a Cartesian plane that has an x and a y. They're real axis. This can't be graphed on a real axis. And so I'm only looking to see what numbers can I input in for x. What can I input in for x that would provide me with answers or outputs that are real? So I want to graph real input, real output. So as I was previously saying, before you could see it, unfortunately I had not shared my screen. There's the number 0, there's positive numbers to the right, there's negative numbers to the left. And we have to decide, is there any limitations? Well, as I just said, I can't plug in a negative because it's not possible to get an answer. For instance, if that doesn't make sense to you, look at negative 25. If you have to think of two numbers that are exactly the same number, same sign in front, it's impossible to find exactly two numbers that multiply to give us negative 25. Yes, 5 and 5 is positive 25, and negative 5 is positive 25. The only way to get a negative 25 would be one positive and one negative, and that does not make them the same value. So, not possible. That means I can't have negative numbers plugged into the square root and to evaluate to get real answers. I'm going to make a little table of values here. X again is input, y is output. Now let's substitute in 0. The square root of 0 is 0. That works. Real and real. Substituting 1. Square root of 1 is 1. Square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. You may notice a pattern here. These are perfect squares. So the next number would be 25 and then 36. Now in the past I've had students that have wondered, why are you not putting down 2 and 3 and 5, 6, 7, 8 and 9 through 15? It doesn't mean they don't exist, but what happens is they don't give us answers that are really pretty to graph. For instance, if I take the square root of 2, it's irrational. It's an ongoing decimal, never stops, and has no pattern. Square root of 3, anything that's not a perfect square, when you take the square root of it, you're going to get the same type of an answer, an ongoing decimal. Doesn't mean there's not an answer, it's just not a nice integer answer. So if I was going to graph those, and I had to kind of make a prediction here, here's 0, 0, 1, 1, 4, 2, 9, 3. It looks something like this, and we're going to do this in DESMOS, so you're going to watch me do it in DESMOS in just a second. Now, what is the domain and range here? Well, domain means x value, so how far does this go to the left? It goes as far as this point. Like this is the starting point. It goes far as 0. This is 0, 0. So x is actually touch at 0, and then there's no limit how far they go to the right. What about the y's? Well, they come down as low as 0 as well. This is domain, and this is range. They come down as low as 0, and then they continuously move up. Not very fast with this original parent function, but they do continue to move up. This is domain and range of the parent function. We're going to look at that together and analyze it together in DESMOS. So in DESMOS here, I'm going to clear the screen and I'm going to type in y equals the square root of x. Now with square root, DESMOS has a little key down here. This is the radical sign, but it only applies for the square root. So when we move on to cube roots later on, there's another way for us to do this, but this is what the square root looks like. And if I did want to show you those points that I just identified, there's 0, 0, 1, 1. Not necessary to do this, but just so you can see 4, 2, and we could go on all the way up to 9, 3, and so on. Okay, we could see those. So let's take what we've already learned about translations. Translations mean how can I move this thing? What does it look like when I move it? So I'm going to let the green represent the original. We call it the parent function. And then anything I add to it is referred to as a translation. So if I take this parent function, and now I'm going to put something inside. Something inside of the radical means we're going to shift it to the left or right. And remember, inside the radical is like inside the parentheses. It's going to lie to you. So if I say minus 3, automatically our brains probably think, hey, I want to shift this to the left 3, but in fact we go just opposite, to the right 3. I'm going to call this the arc of the function. The arc, where you can think of the slope, the rate of the change, it's still the same, nothing's changed. We've just taken it, picked up, and moved it to the right. Likewise, if I did a plus 3, it goes to the left 3. It's the only change. Now if I take that away and I go in back of it, so I use the arrow and I go in back, and now if I add something in back, it tells the truth. That's going to describe a vertical shift. Again, we've learned this, but we're just applying it to a new function. So shift it all up or shift it all down. Okay? Before I move on to the next 2 types that we're going to learn right now, I would like you to go into the chat and either give me a thumbs up or a thumbs down based on your understanding of the first 2 translations. Thumbs up or thumbs down, please. Thank you for those participating, giving feedback. Never ever hesitate to do a thumbs down if you're feeling confused. Okay, here we go. Now, whether you realize it or not, there's a 1 out front. There's a 1 out front. And you may be thinking, I thought there was a hidden 2. Well, that nth root, which is right here, that nth root is different than just a whole number or an integer out front, a 1, okay? But now, if that number in front, we're going to do this with the blue, if that number in front goes anything bigger than 1, we call it a stretch. And watch what a stretch looks like. So we have the green and the blue. They're on top of each other. They're the same. Oh, look at, when I change it from 1 to 2, look what happens. When I change from a 1 to a 3, a 1 to a 4, a 1 to the 5, the higher the number is up front, the larger the stretch. The more vertical it stretches or it rises, the faster it rises. So if I had to describe this number up front, if it's anything greater than 1, we say a vertical stretch by a factor of, and then we name the number. So, for instance, a vertical stretch by a factor of 2. A vertical stretch by a factor of 3. There's often confusion when there's a negative in front. A negative in front does not change whether it's compression or potentially stretch. What it changes is, if I take away the 3 and I change it to a negative 1, we now take what we had in green and we reflect it across the x-axis. So there's 4 different things we're going to talk about here, and I wish that we could put this on pause, but that doesn't work that way. So I'm going to add these in. I'm going to do a plus 2, and back I'm going to do a minus 1, and in front I'm going to do a negative 3. So the order you describe these in, it does not matter. I think it's easier as we visually see it kind of to add these one at a time, and so I'm going to do it that way. I'm going to start with the 2. So inside I had a plus 2, and so we can see that we shifted it first to the left 2. It's opposite of what you think, horizontally to the left 2. Behind it I did a negative 1. That means we're going to take the entire thing and we're shifting it down 1. So I've done a horizontal shift and a vertical shift. Then there was a 3 in front. That means that we take the current slope, or how fast this particular function rises from left to right. And once I change it from a hidden 1 to a 3, we can see it rises at a much faster pace. It's described as stretching by a factor of 3. I know these are things we've all learned with different functions. It's great to review them and now to apply to a different type of function. What happens when I throw the negative in front? Now instead of opening upward, it keeps this place, which I'm going to call it kind of like your starting place, and I'm going to identify it here so there's no confusion. Give me a second. Negative 2. Negative 1. We can see that little dot that I've made there. Okay, that's your starting point. And it says I'm going to stay there at that point. It's like I'm going to put my pencil down at that point. But instead of opening up, as soon as you put a negative sign, it flips open and opens down. We've reflected it down. Okay, it's actually a reflection across the x-axis. With the shift, it's not the x-axis, but without the shift, that's what it is. So we've reflected across the x-axis essentially. Okay, can I have right now, if I provided this to you, this equation to you, and I said, okay, I want you to rate your ability, if time is not a factor, and you can write them in any order, I want you to rate your ability on your own to take an equation like I've highlighted in blue. Could you list for me the different types of translations? And again, if you're confused, could you list to me things like shift to the left 2, shift down 1, vertically stretch by a factor of 3, or reflect across the x-axis? Can you give me a 1 through 5 so that I can see kind of what is our memory of going over this with previous functions, please? So it looks like the average score is maybe about a 4, 4.5. Okay, it tells me you're understanding it. So I do want to describe to you what's going to be happening today. You have two types of functions, and we started with the easier of the two. So what's going to happen today is you're going to get a function and you're going to plug it in. I'll give you an example. Let me make up a function here. We're going to say this is number 1 in your homework. It is not, but we're going to go with it. This is number 1. So the first thing you're going to do, there's 4 steps to every homework problem. The first thing you're going to do is you're going to put it into DESMOS and you're going to graph it. That's step number 1. And then the second thing I want you to do is I want you to see with square roots, I want you to decide where is that start point. Okay, and you can click on the graph to see. You don't have to do this, but for the purpose of me explaining, I'm actually going to label it for you so you can see it. So my start point is 2, 3. 2, 3. So the first thing is we graph it. The second thing is we're going to identify where that start point is. Now I'm going to flip over here. The next three things, and the order you write these in doesn't matter, are going to be what's the domain, the range, and list the translations. So the domain here, the x values start at 2. Remember, this is x, this is y. This is domain, this is range, how it describes. So x's start at 2, and there's no limit how far it goes to the right. The range has been shifted up 3, so it starts at 3. There's no limit how high it goes. And then in any order, you would list this off. In any order. Order does not matter. So we'd say things like shift up 3, shift to the right 2, and stretch by a factor of 5. Okay, can I have right now, can I have a thumbs up or a thumbs down? Give me 1 second to get into Teams on my phone. I can hear it buzzing, but I want to make sure I'm seeing your. Okay, I'm getting thumbs up from everybody that has provided me with feedback. So that's what you're going to do with square roots. Now we're going to do the exact same thing with a function that you probably have not been exposed to, and that's cube roots. So I'm going to start by talking about what is cube roots. This is square roots. What is cube roots? What does it look like? Is there any limitation of where I start and where I move with this? And then we're going to practice. So cube roots. So cube roots look like this, and the nth root is 3. Now, what does cube roots mean? Let's talk about that. We talked about what square roots mean. Let's just give you an example. Let's say if I asked you to evaluate this, how would you do that? Well, you would pull this out, and you'd find in the third column, cube root of 3, find the 8, and I know that it says negative 8, but we're going to come back to that. You'd find 8, you go straight across and go, okay, I need to start with 2. I need to check this out with 2. So I write down 2, 2, 2. If I multiply 2 times 2 times 2, I get 8, but I want a negative 8. These have to be exactly the same. It can't be like one's negative and the other 2 are positive. They have to be exactly the same. If I make them all negative, well, 2 times 2 times 2 is still 8, and look, there's an odd number of negatives. When you're multiplying or dividing, you can count how many negatives. If you have an even number, your final answer should be positive. If you have an odd number, your final answer should be negative. So this works. If I evaluate it, I get an answer of negative 2. What does that tell us? It tells me that I am allowed to plug in negatives. Remember, with square roots, it didn't work. Square roots didn't work. But cube roots, because there's an odd number here, cube roots, I can plug in negatives. So when I make my table, I don't have to start at 0. I can do negative 8, negative 1, 0, 1, and 8. Let's try this. So I've already evaluated the cube root of negative 8 is negative 2. And I will tell you it's probably easier for you to start at 0. If I plug in 0, what's the only number I can take times itself 3 times to get 0? The only number you can do is 1. Then I'm going to start with 1. So I find the cube root column, and I go to 1, and I evaluate it to see 1. Then I find 8, cube root 8, and I evaluate it to get 2. And know that when we go backwards here, it's the same pattern, just everyone has a negative. So negative, negative, excuse me, that's a 1. Negative, negative, and negative, negative. What shape does this make? Students have often described this as kind of like a lazy looking S. It's kind of like a slumped over S. So we think of S's like this, right? But if I make it kind of like lazy looking, it looks more like that, right? If I pull it apart. And that's what this looks like. Here's 0, 0, 1, 1, 8, 2. -1, -1, and 8, -2. So it looks like an S that we've kind of pulled apart, right? S's are like this, and I've kind of taken these two ends and I've pulled it. That's the basic shape. Now here's the cool thing about cube roots. When it's time to do the domain and range, your life is easy. Because even if we translate this thing, that means even if we move it up, down, left, right, we reflect it, look at, there's no limit how far it goes to the left, and there's no limit how far it goes to the right. So the domain is always negative infinity to positive. And the range is the same. There's no limit how high this goes, even though it's increasing really slow, it's still increasing. And there's no limit how low it goes, even though it's decreasing low. So the domain and range for cube root functions, when it's time to do those, automatically done. You can put this in and you're done. Because the domain and range, there's no limitation what comes in, there's no limitation what goes out. No restrictions. This is your domain and range for all cube root functions. Okay, let's talk about what this looks like if we start to do translations with it. So I'm going to go back up here. And remember, this is a square root. And so it's a specific type of radical. Now with cube roots, what I really wish is I wish that this particular program, DESMOS, would allow us to put like a little 3 right there. It doesn't. So we have to put it into rational exponent form, and you learned about that. You learned about how to rewrite it the first lesson of this unit. So for instance, we can rewrite this. You'll see this AB here. Click on the AB, and it's not to the third, it's to the 1/3. Remember that nth root always goes in the bottom. So this is, when I click off here, this is that basic S shape. It's that basic S shape. So look, here's your 0, 0. We just talked about that. We should go, here's 1, 1. Ooh, find it here. There's 1, 1. I should be able to go over 8 and up to 2. Okay, same thing. I should be able to find -1, -1, and -8, 2. Great. But how do we translate this? It works the same way that all our other functions do. Anything inside means we move it in the opposite direction, left to right. So if I do a +3, I've taken the whole thing and I've just shifted it to the left 3. Behind it, if I do a -2, I've taken the whole thing and I've shifted it down 2. Now if I put a number in front that's greater than 1, never equal to 1, but greater than 1, we're going to notice a huge stretch here. Notice how high and how fast it goes up and how fast it also goes down as we go to the left. So the smaller, or sorry, the larger the number, the faster it goes, and then the smaller the number, we can see that, wish I could bring this down here. As I bring this number back down closer to the 1, it becomes closer and closer to that parent function until it's at 1. Now what if we go below 1? Well, between 0 and 1, it just is going to flatten out. So it's going to be even flatter, right? It's just going to be, it's almost going to look like it's a flat line to the left and the right as we go further out, but it is still increasing just at a slow pace. And if that number out front would have a negative sign, then instead of going up to the right, it's going to go down to the right. Instead of going down to the left, it's going to go up to the left, and I'll show that now. So it's just going to flip places. There we go. Okay, you ready? So let's start with 1. Let's say I provided you with this equation here. And I'm always going to ask the same thing. What's the domain, what's the range, and what's the translation? Okay, it's important to practice putting into DESMOS and that you have an opportunity to see what it looks like. That also leads into what we're going to be doing a little bit on Friday. But domain and range, remember I've made it clear. 1, it's cube root, and only cube root, it's really easy. Domain and range is exactly the same. There's no limitations. Now, could you do the translations without graphing it? Sure, you could. So you could write to the left 4, down 1, vertically stretched by a factor of 2. Sure, you could. Some students have asked me, how do I know if it's a square root or cube root? If it's a cube root, you see a 3 here. If you don't see a number, it's a square root, or it may be a 2 there, but if you don't see a number, it is a square root. So translations you could write out, and you wouldn't have to look at the graph. But I do prefer that you graph it so you can practice. So I'm going to come up here. In front, I'm going to put a 2. Oops, sorry. Inside, it's going to be a +4, and in back is a -1. And so this is what it looks like. Again, shifted it left 4, down 1, and it is rising and falling at a faster pace. Can I have right now a 1 through 5 and how well you're feeling about this? 1 through 5. So let me describe what the homework is going to look like today. Despite what the directions are, if you were, and I was unable to change the directions on the actual document, it's in a PDF form, so I'm unable to change it, but you are going to be doing the same thing every time. So I'm going to come back up here so you can see, same thing every time. You're going to see a problem. You don't have to graph it in your notes. You don't have to do that. You're going to write down the domain, the range, and then the translations. Remember, a common misconception is students think they can just write this down always. That's only with cube roots, not with square roots. Square roots, you're going to graph them to see where does it start, okay? Where does it start? Okay, that's with square roots. Cube roots, you can just put this down. So your homework looks like this. I'm going to share the screen with you right now. Give me 1 second. Wrong one. There's quite a few problems, but again, they probably take about 30 seconds to do each problem. So here's the problem. Again, we can already state the domain and range because we know it's a cube root. You don't have to grab it, despite what it says, and then you need to tell me the translation. So you would say shift to the right 2, shift up 1, and you'd be done with this problem. Thumbs up if you're understanding, and thumbs down if you're feeling confused. Thumbs up if you're understanding, thumbs down if you're feeling confused. Okay, so it is 11:07. I want you to do everything in your power to have this done by 12:10. When 12:10 is approaching, it's 12:05 and you're still not there yet, let me know. We can make some modifications. I want you to give yourself a 3 or 4 minute break. This assignment can be found by looking up into the assignments, and it does say graphing radical equations. You're doing it in your notes. Again, you're not graphing on paper. You're doing domain, range, and translations. When you're done, you upload it. Let's see if you can have that done by 12:10. Thank you guys for being present in class today, and I will provide you with this video as well. Let me just come back to it so I can stop it.